Section 5.8, Inverse of Matrices. Now, so far, we've seen several properties of matrices. We did that in section 5.7. We looked at, for instance, the addition, the subtraction, multiplication. Remember, there is no division property of matrices. We look at those and how they parallel with operation on real numbers. So in this section, we're going to yet look at a couple of more properties of matrices that draw very near to identity property and multiplicative property of real numbers as well. So these are a couple of properties. So to recall them, first of all, with the real numbers, we know the identity property of real numbers. 1 serves as the identity. 1 is the identity because 1 times any number is the number itself. So a times 1 equal a, and 1 times a is equal to a. That is known as the identity property of real numbers. Now with matrices, there is this identity matrix that we will talk about in a moment, but I just want to show you the properties, that how they draw parallel to each other. So you multiply any matrix times the identity matrix, you get the matrix itself, or identity matrix times A gives you A. Notice generally in previous section I mentioned AB doesn't equal BA, right, in general. But in the case of identity matrix, actually that property holds. AI will equal to IA. So you can pre or post multiply a matrix by the identity matrix. And then we have the multiplicative inverse property with real numbers. The multiplicative inverse of A is a number 1 over A, which we can write with negative exponents as A to negative 1. It is multiplicative inverse because the product gives you 1. Now with matrices, if a matrix is A and its inverse, we call it A inverse, using the same notation as we did with real numbers. Then we can multiply these two matrices. A inverse would be the identity matrix, IN. And also if you do A inverse A, in this case, you also get the identity matrix. So pre or post multiply the matrix and its inverse are allowed in this case. So what does this identity matrix look like? Well, for one thing, the matrix is a square matrix. So a second order identity matrix means a 2 by 2. It looks like so. There. We have 1s on the main diagonal and 0s on the off diagonal. We looked at the identity matrix indirectly. Remember when we did when we talked about solving equations, systems of equations by matrices, we did Gaussian elimination and Gauss-Jordan elimination. We found similar pattern in the final matrix in a reduced row echelon form. We saw the same pattern of 1 0 0 1 pattern, but the focus is just on the identity matrix here. So this is again a 2 by 2 identity matrix. If I have a 3 by 3 and order 3 identity matrix, so this one looks like 1 0 0 1 0 1, and then you have zeros above the diagonal. So it's made up entirely of 1s and 0s. This is a order 3 identity matrix. So what does an n by n identity matrix look like? So you can imagine you have n 1s along the main diagonal and you have 0s elsewhere. And there you go. And this one's 0, so on and so forth. This last one is supposed to line up with the 0 here, and there you go. And this continues on, so you have 0 0 all the way here. Now in the middle here, somewhat you have the aij, the ith row jth elements. But remember, the main diagonals have to be 1s, just like here, and 0s on the off diagonals. So that is an n by n identity matrix. Okay, so the Aij here that I have written, by the way, in the middle of that matrix, that Aij, the Aij here is going to be 1 whenever the diagonal elements are 1, right? So that would require that I and j will have the same index. So for example, this is in this example for a 3 by 3. This one is in the first row, first column. So that's A11, A22, A33. If it was 4 by 4, the next one would appear at A44. So as long as the subscripts are the same, the I and j, then the value is 1. And if the subscripts are different, they're not equal, then the value would be 0. And that's how you interpret this Aij in the middle of this identity matrix again. And let's say that's when I is different from j. This will give you the off diagonal elements. All right. Now, we want to emphasize again, the matrix times identity matrix in either order will give you the matrix itself. All right. Now, something that's interesting about the identity matrix here, if, for instance, if I have an I2, okay, which is 1, 0, 0, 1, it is possible to square these matrices. And when you square them, let me just show you, to square that matrix, that means you're going to multiply by itself, right? Twice. So I'm just going to do 1, 0, 0, 1 times it by 1, 0, 0, 1. And if you do, the product's going to be a 2 by 2. Multiply first row, first column to get the element in the first row, first column of the product. Do 1 by 1, 0 by 0, that's 1. Okay, to get the number in the second row, first row, second column. I'm going to do first row, second column, multiply the corresponding elements. So that's going to be 1 by 0, 0, 1, and that both of those are 0. When you add, you get 0. Kind of see where this is going, right? And let's get the element in here. This would be second row, first column. Multiply 0 by 1, 1 by 0. Again, that product would be 0. And when you do element in the second row, second column, you'll be multiplying 0 by 0 plus 1 by 1, which gives you 1. And lo and behold, you get an identity of order 2. True? So if we do I cubed, again, you get exactly the same thing. So any order identity to any power, to the mth power, is going to be in. That's a very interesting property of identity matrix. That would be equivalent to like 1 to the nth power equal 1 with real numbers, right? Let me make that m there. So again, you see another parallel between real numbers and identity matrix. So now let's see how we're going to find the inverse of a matrix. Okay, the multiplicative inverse. So the best way to do this is to go through an example. So we want to find the inverse. For one thing, to find the inverse of a matrix, the matrix must be square matrix. Okay, if a matrix is a square matrix, its inverse may exist. So let's see how this is going to work. And there, I have some matrix here. It's a 2 by 2, so its inverse is going to be 2 by 2 also. So how are we going to actually find this inverse? Well, to do this, we're going to form the augmented matrix A augmented by the identity matrix of a similar order. So in other words, for my example, I'm going to augment A in a moment with a 2 by 2 identity matrix. And then we're going to transform this augmented matrix in a matrix that has identity matrix. And then we have the line, and it's the matrix on the other side of this line. That's also augmented, but through transformations, this is how we would want this to look like. Okay, so we're going to transform and get it to look like the one on the right side here. And when we do, we're looking at the inverse matrix. So let me do an example, the one that we're doing, 2, 4, 1, negative 1. First, we're going to augment it, right? So it's going to be 2, 4, 1, negative 1, augmented with 1, 0, 0, 1. Now the focus is on the elements over here on this matrix. We're going to transfer this matrix. We're going to turn it, use like a reduced row echelon form. Let's do our manipulation with matrices. Remember the elementary operation with a matrix. You can multiply, you can switch rows of a matrix. You can multiply any row by a non-zero constant, and you can replace a row by the sum of that row and a constant multiple of another row. We have 3 of these operations that are, I believe, in section 5.2 of this chapter. We addressed it. Feel free to watch that video if you need to in section 5.2. All right. So let me do this. What I'm going to do then, I'm going to do the following. I went ahead and did negative 2 times row 1, added it to row 2. Let's see what happened. Oh, and also, let's see, I actually switched first row and second row first. So let me do that first. I swapped the rows. R1 exchange with R2. So this gave me 1 minus 1, 0, 1. Notice the entire row, even the 0, 1, move up to the first row. Switch with 2, 4, 1, 0. Okay. Next, to get a 0 in this position, what we're thinking is this again. Remember, we want to get 1, 0, 1, 0, 1, 0 in this formation. So I need this 2 to become a 0. So how I'm going to do that, I'm going to use elementary row operation on matrix, operation number 3, which is I'm going to multiply negative 2 times row 1 actually and add it to row 2. Now in this operation, remember the first row is a helping row. That's not going to change. It's the second row that's going to change, and that's going to make it negative 2 times the first row. Let me do that. That's this one. So it's going to make it negative 2, 2, 0, negative 2. Correct? That's negative 2 times row 1. Add it to existing row 2. And we're going to get 0, 6, 1, negative 2. All right, 0, 6, 1, negative 2. So we got the 1, 0 pattern here. Next, I need to get a 1 in a place where there is a 6 right now. So let's do that one. How am I going to do that one? I'm just going to multiply second row by 1/6. So I'm going to do 1/6 of R2. Seems like a lot of work just to get an inverse, right? I'll show you at the end. I'll show you after this, in fact, maybe. A quick way of finding the inverse of a 2 by 2, and that's really what I'm personally interested for this course, the college algebra course, because we just want to give you some just expose you to some of the topics here. We're not going delving too deep into these topics, and chances are, again, even if you want to find the inverse matrix ourselves, we don't do this by hand anymore. We use technology. So just to give you some exposure to the topic, this is good enough to kind of see the misery that's involved in doing this the old-fashioned ways. So 1/6 times row 2 is what I'm doing. 1/6 of 0, 1/6 of 1, 1/6 of 1/6 of 6 gives me 1. 1/6 of 1 is 1/6. 1/6 times negative 2 is negative 1/3. All right, so the right side of this matrix, this side is beginning to change. as the left side is looking like it's reduced row echelon form. So what do I do to get rid of the -1 in the first row? Let's just add row 1, row 2, and replace row 1. So row 2 is going to be unchanged, 1/6, -1/3. Row 1, 0 plus 1 is 1, 1 minus 1 is 0, 1/6 and 0 is 1/6, 1 minus 1/3 is 2/3. See how we just added the elements in columns. And there we have it. We did actually achieve what we wanted to, right? Remember, we want to accomplish this, and we did. At this point, I do have this structure that was proposing earlier. The matrix, the 2 by 2 matrix that's on the right side now, we claim that to be the inverse of the matrix, of the original matrix A, which was 2, 4, 1, -1. You see how that works? Therefore, I can say if A is 2, 4, 1, -1, its inverse turned out to be 1/6, 2/3, 1/6, and -1/3. All right, now how do we know if we got the right inverse? If this is true, these two matrices are inverses of one another. The way to check this is to do the following. If I do A inverse, or A inverse A, these are 2 by 2, so the product is defined either way. Let's multiply them. So I'm doing a 2, 4, 1, -1 multiplied by 1/6, 1/6, 2/3, -1/3. So if I'm multiplying them this way, like that, I'm going to multiply again first row by first column to get the first row, first column element. That gives me 2/6 plus 4/6, right? Multiply this by that. First row by first column. And then I do first row, second column. That's 2 times 2/3 is 4/3 minus 4/3. And you can see that becomes 0. True? Let's try this position. In that position, we have second row, first column. So I'm going to do second row, first column. 1 times 1/6, -1, -1 by 1/6. Those become opposites, but let me write it anyway. That's 1/6, -1/6. All right, and finally, I can write second row, second column. 1 times 2/3, -1 times -1/3. That's going to be 2/3 negative of -1/3. Cool. And we have the product. Next, I'm going to just, I can do it in here. Let's just combine the fractions. 2, 6, 4, 6, that's 6, 6. That's 1. Next to that, 4/3, -4/3, they're opposites. They add to 0. And the lower left, opposites add to 0. And the second row, second column, -1/3 is a third, 2/3, and a third makes 1. And here we have it. And finally, what we're going to get is the outcome we were expecting. We get an identity of order 2. And that should always be the case if we have found indeed the correct inverse. Now, I did mention that I'm going to show you a way to do this much faster. This works for a 2 by 2, by the way. Okay, so let me just say finding A inverse for a 2 by 2 matrix. All right, and here's how it works. Suppose A is a matrix given by A, B, C, D. Suppose we have that. We can find the A inverse this way. We can go 1 over determinant of A. Remember, we talked about determinants in section 5.3. If you need a review of that, please watch that video. And then what we do is we actually swap out the diagonal elements. AD becomes DA. And then the off diagonal elements, we just simply change the sign on those. Don't swap them. Don't change them like we did A and D. Simply change the sign on them. Okay. And there you go. You're looking at the inverse. So for example, the one we just did, let's do 2, 4, 1, negative 1. Okay. We're doing 2, 4, 1, negative 1. We want to find the inverse. So A inverse would be 1 over the determinant. Remember, determinant of a 2 by 2 is when you multiply the diagonal elements minus product of the off diagonal. That's negative 2 minus 4, which is negative 6. That's my determinant. And then all I have to do is switch 2 and negative 1. Don't change the sign on them. We just swap them. We swap these two elements. All right. And then change the sign on the off diagonals. Don't swap them. We swap the diagonals, but we don't swap the other ones. These two we don't swap. We just change sign on them. And there you have it. Let's do 1 over determinant, because determinant of a matrix is going to be a real number, right? So this is going to give me a real number, which real numbers in matrix terminology, we call them scalars. So I'm doing a scalar multiplication of 1/6, negative 1/6 by every element of that matrix. So it's going to make it, so you're going to, it's like distributing it to every one of them. Okay, so what is it going to be? It's going to be negative 6 times negative 1. That's going to be 6. And oh, sorry, it's 1/6. It's 1/6 times 1, so it's 1/6. Then negative 6 times negative 1/6 times 4 is 2/3. Negative 1/6 times negative 1 is 1/6, and negative 1/6 times 2 is negative 1/3. And that's exactly what the inverse is up there. See, 1/6, 1/6, 2/3, negative 1/3. 1/6, 1/6, 2/3, negative 1/3. So they're the same. Okay. Now this is actually a good place maybe to mention something, and I did mention that in passing in the beginning, but I probably said it too fast. The inverse of a matrix doesn't always exist. Okay, just because I have a matrix doesn't mean it has an inverse. And you can kind of see that in this formula. It's embedded in this formula how it may not exist. If the determinant of a matrix is A in this approach, in this process of finding the inverse, if the determinant is 0, right? If determinant of a matrix is 0, then I have 1 over 0, which is undefined. That means the matrix does not have an inverse. Okay, so how can the determinant of a matrix be 0? Well, one of the ways the determinant of a matrix could be 0 is this. Let's say I have 1, 2, 3, 0, 0, 0, 4, 5, 6. Is when one of the rows or one of the columns of the matrix may be 0, right? So in the case of, let's say, if this was a system of equation that had 3 equations, 3 unknowns. If I have a row of 0, that just signals that the system is a dependent system. That means the equation in the system, one could be a multiple of the other. So that is why the inverse may not exist. Okay. So in this one, if determinant is 0, then A inverse does not exist. Okay, and that's in general true for any size matrix. Okay, now let's take a look at another example where we want to find the inverse, and we're going to find it rather quickly using this method. So I have 2, negative 3, 1, 5, and I want to find the inverse. So again, the inverse is 1 over determinant. The determinant of A is 2 times 5 minus negative 3 times 1, right? We go products like that. Diagonal minus off diagonal. That's going to be 10 plus 3. So the determinant is 13. That's going to be 1 over 13. Look how fast we get this. Swap 2 and 5. We get 5, 2. Change negative 3 to 3. 1 to negative 1. And there you go. We're done. You literally spend less than a minute to find this inverse. And of course, you can distribute the 1/13th. We should, because it's going to be a matrix, right? So the answer is 5/13, 3/13, negative 1/13, and 2/13, because the result is a whole matrix, not a scalar multiple of a matrix. And there we have that one. Okay. Now, the last idea of this section, and then we'll be done with the chapter, is actually solving systems of equation by matrix, inverse matrix, that is. Okay, so let's see how that works. Looking at solving systems by inverse matrices. So let's see how this works. First of all, suppose I have a system. The general form of our system is going to be a11x plus, let's say, a12y plus a13z equal b1. So we're going to make it 3 equation, 3 unknowns. But this extends, by the way, to higher order systems. a22y and a23z equal b2. And the third equation will be a31 plus a32y plus a33z equals b3. So I do have a system of equations here. All right, with the system of equations, then I'm going to write the matrix of coefficients on x, y, z. Those would be a11, a12, a13. See how the pattern is exactly like the pattern that we looked at when we started the previous section. We talked about matrices in general. And there you go. A31, this would be A32, and A33. This is what we call the matrix of coefficients. So let's call this A, because it's made up of all A's, times. And the variables are X, Y, Z, right? We're going to call that the matrix of variables, X. In this case, I have a 3 by 3. And the variables are 3 by 1, 3 rows, 1 column. So the multiplication is defined because the inside numbers are the same. The size of the final product matrix is going to be the matrix of constants on the other side of this. That's going to be a 3 by 1. Okay, so this would be the general matrix form of a system of 3 equations, 3 unknowns. What's important for us is this 3 by 1. Now we can combine this expression and write it as AX equals B. That's the general form of a system where A, capital X, and capital B, all 3 of these are matrices now. Okay, so to solve the system, I'm going to say suppose the inverse exists, right? In other words, suppose this has a solution. If it's inconsistent or dependent, then we have to use a different approach. So if the inverse exists, by the way, we say that A is invertible. In other words, A is invertible. So suppose I can find its inverse. Well, if we can, then let's pre-multiply both sides by the inverse. And that would be A inverse B. And remember, we just said A, B does not equal BA earlier in our lectures. In general, that's not true unless A or B are identity matrix. Okay, and in fact, we did talk about this when we talked about, in this lecture, when we talked about the identity matrix. So, because A inverse B does not equal to be A inverse. All right, so you got to be careful because I pre-multiplied, right, before AX, I pre-multiplied by A inverse, then I'm multiplying, pre-multiply B by, I guess it's called post-multiplication. That's okay. So I'm post-multiplying AX by A inverse. All right. So I'm multiplying from the left. How's that? It's got to be left on both A inverse on the left and A inverse on the left of the other side of equation. Now, I can combine A inverse A. Remember the associative property? This is where that would come in handy. In the beginning, I was doing this step. Next step, I'm changing the association. This is going to be A inverse B. Now, any matrix times its inverse in any order will give you the identity matrix, right? So this will give me an identity of order. It will be 3 by 3 times X equals A inverse B, and X is equal to A inverse B. All right, so we just kind of proved how to solve for the system. If a system is in the form, in general, AX equals B, then the solution to X is when you multiply, post-multiply B by the inverse. Okay. Now, again, this is assuming that the inverse does exist. So let's see how we're gonna work this one. In my example, suppose that I have a system, a system of equation, and the system is negative x plus y equal 1. And let's make this one 2x minus y equal 1 also. So what are the a, x, and b here? Well, A is the matrix of coefficients, negative 1, 1, 2, negative 1. X is a matrix of variables. In this case, I have only x and y. And B, the matrix of constants, 1, 1. Okay, now once I have this, well, let's see, the solution to AX equals B is X equal A inverse B, right? So in other words, I need to find the inverse of the matrix, and I'm going to find it the easy way. A inverse is going to be 1 over determinant of A, right? 1 over determinant of A, let me just put it one more time, times, to do this, yeah, that's fine. I'm going to switch the elements, right? Negative 1 switched will be the same. It stays negative 1, negative 1. And then change the off diagonal, the sign on those. Remember, we just did using this formula. What is determinant of A in this exercise? Determinant of A is negative 1 times negative 1 diagonal minus 1 by 2 off diagonal. That's 1 minus 2 or negative 1. So this gives me 1 over negative 1, which is negative 1 times this matrix. And of course, 1 over negative 1 is negative 1 times everything. We would simply change the sign on this to 1, 1, 2, 1. And that would be the inverse of the matrix. True? That's A inverse. Now, the solution to X is A inverse. That is 1, 1, 2, 1 times B. B is 1, 1, right? B is up there, 1, 1. And now we can multiply. This is a 2 by 2. So 2 by 1. Inside numbers are the same. Outside numbers will be the dimension of the product, which is a 2 by 1. Right? And we expect 2 variables for this one. 2 equation, 2 unknowns. So what is the number in the first row, first column? You multiply first row by first column, do 1, 1, 1, 1. The product is 1 plus 1, 2. Okay. And then the element in the second row, first column, the second row, first column. So we get 2, 1, 1, 1. 2 times 1 is 1. 1 times 1, 1. 2 and 1 makes 3. Okay. So there we have that one. And that is a solution. Isn't that cool? So that's how the matrix method works. So using inverse of a matrix to do this. Let's do one last example and we'll be good to go with this section and we'll be done with the chapter. So my system, 2x negative 3y equals 4, x plus 5y equals 2. Notice I'm only doing 2 by 2s here, not 3 by 3s, 3 equation, 3 unknowns, because finding the inverse this way will take time. So we'll just focus on 2 by 2s. A is going to be the matrix of coefficients 2, negative 3, 1, 5. X, the matrix of variables. That would be, I have x and y in this. And B, the matrix of constants. The constants on the other side of equal sign are 4, 2. The solution to the matrix, right? The matrix of unknowns, the solution to the system, I should say, is going to be equal to A inverse B. So how am I going to find the inverse of the matrix? A inverse, again, 1 over determinant. I'm just going to do this. The determinant 2 by 5 minus negative 3 times 1. 2 times 5 minus negative 3 times 1. And then we're going to switch the diagonal elements, right, of 2, 5. It's going to become 5, 2. And then we change the signs on the off diagonal elements. Now, the denominator, which is the determinant, is going to be 10 minus negative 3. That's 13. And we have 113 times 5, 3, negative 1, 2. And there is the inverse. Now, we can actually multiply now. X is equal to A inverse B. And I can write this as the A inverse is going to be the 1/13th. I like to keep that factored. Right, because we can multiply 1/13 by the elements. And let me do it on the inverse side here. So everything will have a denominator of 13th, right? And that's going to be 3/13, and that's going to be 2/13. So that is truly the inverse matrix. Now, it'll be easier for me to keep the scalar 1/13 outside of the matrix and only do it as whole numbers or integers 5, 3, negative 1, 2. So the integral values or integer values are easier to work with. That's the rationale for doing this. So we're doing a 2 by 2 and a 2 by 1. The product's going to be 2 by 1. And here it is, 2 by 1. Let me actually put details on this one. This will be a 2 by 1. You're going to multiply first row by first column. So I'm going to do 5 times 4 plus 3 times 2. Okay. My right bracket, square bracket's too far. All right. The element in the second row, first column, we're going to multiply second row by first column. So we do negative 1 by 4 plus 2 by 2. And this is going to give us the final answer. Going to be 1/13 of 10. I'm looking at that product. The arithmetic, 5 by 4 is going to be 20 plus 6 is 26. And the bottom, second row, negative 4 plus 4 is going to be 0. Right? Now multiply the scalar. 1/13 times 26 makes it 2. 1/13 of 0 is 0. And we are good to go. The system has a solution. And the solution is 2, 0. Remember, this was the matrix of X. And X is XY. So we can say the matrix of variables equals to the matrix of the answers, the solutions. And from this we get x equal 2, y equals 0. Remember, two matrices are equal if corresponding elements in that position are equal. And that's it, folks. We're done with this section, and we're done with the chapter indeed. So section 5.8 is out solving system using inverse matrices. I hope you find this useful, and you should be able to do your homework now. As always, thank you for watching, and be safe wherever you may be.